So this kind of question, we have to analyze what we have. So we start to notice that we have a product. It is fish. That has something to do with the heat capacity that differs between different kinds of products. We notice how much. We also notice that we are starting below its freezing point. So there is something here we have to take into consideration. So if we start to make a diagram just to sketch the situation. So we make a diagram here with temperature and heat added. Then we start with we have minus 18. That's where we start. And from minus 18 we are heating up until the freezing point. So the temperature will rise. Then we reach the freezing point, and we will look up in tables that the freezing point, that is minus 2. And we can see that by going into the table of the products that we are looking at. So the freezing point of fish is 2 degrees centigrade. So that is the first thing that we have to notice. We could, for example, write it into a table like this to get an overview of what we are looking at. But anyhow, we are having minus 2 degrees here. So minus 2. And as we know, when we continue heating something and it is changing phase from frozen to thawed, then the temperature is not changing during a phase change. So we are adding energy, but the temperature are not rising. When everything has melted, then it heats further until 5 degrees. The scale here are not correct, but you will know the picture here. So the temperature rises during this phase change. And we have two different types of heat that we can supply. One, or not two different kinds, but they are calculated differently. One equals mass of product times the increase in enthalpy. This is during a phase change, so we can see there are no temperature involved here. So that would be the thawing from minus 2 and up till it has finally melted. The other type are using a temperature change. So that is also the mass. Then it is the specific heat capacity. And then it is the change in temperature. So if we look at these two different types of heat that can be added, then we can see here that the first stage here, that could be, that we could call that Q, what should we call it? Q heat. That equals down here. So that must be M Cp delta T. The next stage here is Q thaw. That would be mass times the heat of fusion. And the last step here, Q equals again M Cp delta T. So the strategy for solving this is to look at the different steps in the process and looking at each different change at a time. So this could be I don't know what we should call it. Fridge. Probably a bad word. Anyway, these are the 3 steps that our fish are going through while it is being thawed in the refrigerator. And then we simply add the different contributions. So if this was 1, this was 2, this was 3, then Q total are Q1 plus Q2 plus Q3. Okay, so Q1, that was heating from -18 up till -2, or defrosting or whatever. I think it's a wrong word. It's probably not an accurate word, but that's what we call it now. So Q1 equals mass times the specific heat capacity times the change in temperature. And the mass were 1 kilo. The heat capacity below 0, because as we can see here, we are below, or not below 0, but below its freezing point. So if we go to the table here, look for fish, and we look for the specific heat capacity, then below freezing, that is this column, then it is 1.67. So we have 1.67 kilojoule per kilo per Kelvin, or degrees Kelvin. It could actually also be degrees centigrade, because it is a relative temperature. So we say per degree centigrade, and then delta T. So that is delta T here is the maybe we should, how could I write that? If we make a small box here, delta T equals T2 minus T1. So that means that we go from the end temperature minus the start temperature. So the end temperature are -2. So the delta T are -2 minus -18 degrees centigrade. So that gives us 26.72 kilojoule. And we note that the units hold here, that the kilos cancel with kilos. The increment in temperature cancels with the increment in temperature. Then we have kilojoules left here. So Q1 is done here. Q2. So Q2, that would be the mass times the heat of fusion. And the mass were still 1 kilo. The heat of fusion are also found in the table here. So we can see here that the latent heat of fusion for fish is 276 kilojoules per kilo. So that is 276 kilojoules per kilo. And when we do this calculation, then it is also 276 kilojoules. The units cancel. We have kilos and kilos, so we have kilojoules left. So Q3 equals M times Cp times delta T, 1 kilo. Cp, now we are above the freezing point of the fish. So at this stage, Q3, the specific heat capacity are now a different value. So we go to the table here, and we see that specific heat capacity above freezing point. So that is this column here. Then it is 3.18. 3.18 kilojoules per kilo per degree centigrade. And when we calculate that one, that gives us 22.26 kilojoules. And again, the units cancel out here. Oh, I forgot something. I'm sorry. I forgot we need the delta T, of course. Delta T. So times end temperature was 5 degrees centigrade minus 2 degrees centigrade. So that is 7. So that ends up with 22.26 kilojoules. So that was good that we remembered the units, such that the degree centigrade for the change here actually also included. That's why we always want to control the units, such that we know that we don't forget stuff. Okay, so Q total is now the sum of these three. So Q total equals these three that we got up here: 26.72, 276, 276, and 22.26. That gives us a total of 324.98 kilojoules. So this is what is that are saved by thawing it in the refrigerator. Okay, so now the second half of the question, maybe I should move that up a bit further. Now this fish are taken out of the refrigerator and are put into a pot containing water, and it is a stainless steel pot weighing 1 kilo. There is a starting temperature. Now we are told that it is heated to boiling at atmospheric pressure. Also, we are told that 200 grams of water evaporates. So now we want to analyze once more what is going on. So we are basically having the fish. So let's say that we have Q fish, because the fish meat is heated to boiling point. It is a process where we go from 5 degrees to 100 degrees. So Q fish will be, sometimes I just make this slanted line just like the diagram up here. But now we only have the diagram where we go from 5 and further up here, up until 100 degrees. So this part of the line, this dotted part, sometimes I like to just draw that. So we have a mini chart here. So we go from 5 to 100 degrees. So we can see we have no phase change here. That means that Q fish equals the mass of the fish times the heat capacity of the fish times the temperature change. And that equals 1 kilo times 3.18 kilojoules per kilo and per degree centigrade times delta T, 100 minus 5 degrees centigrade. So that equals 302.1 kilojoule. 0.1 kilojoule here. And units cancel, centigrades, kilos, leaving us kilojoules. So Q fish are taken care of. We also have a pot that are heated. So Q pot, the pot went from 20 degree to 100. So Q pot equals 1 kilo, because that was what the pot were weighing, times, maybe I should start with just the symbols here. Mass times Cp times delta T. And that equals, the mass were 1 kilo. Cp for steel. Then we go to the tables here and we say that we have a specific heat capacity for stainless steel 0.48. So that is 0.48 kilojoules per kilo per degree centigrade. Then delta T, we end with 100 degrees, the pot were 20. So, and that was, sorry for the sloppiness, degrees centigrade, equals 38.4 kilos. So that were the pot. Then we have the water. And now we have to be careful because the water are heated, but some of the water are also evaporating. So we have water that rises from 20 to 100 degrees. So Q water equals mCp delta T. So how much water was it? Was it 1 kilo of water? Yes. Someone chose some nice numbers here. 1 kilo of water times the heat capacity of water, and we found that here. Heat capacity above freezing 4.19. So we write 4.19 kilojoules per kilo per degree centigrade times delta T, which were 100 minus 20 degrees centigrade, 334.4 kilojoules. Always check the units. Centigrade, leaving us with kilojoules. Yes. Now comes the tricky part, which is not tricky, but we just have to remember it, that some of the water evaporates. Q evap. So evaporation are a phase change from liquid water to water vapor. So that is actually a flat line, like in the diagram. So there are no temperature change here. So Q evap equals mass of water times the latent heat of fusion. And those are also table values. So we go here and say the mass of water were 200 grams, right? 200 grams of water. But we want everything in kilos. So that is 0.200 kilos times the delta H of water. So we go to the tables and scroll down here. And now what we want to understand is that it is at atmospheric pressure. The water boils at 100 degrees centigrade. So we go into the steam table where the column is sorted for temperature. And then we want to find the position where we have the enthalpy for evaporation, which is here. So we have 2257 kilojoules per kilo. So that gives us 2257 kilojoules per kilo. And that is equal to 451.4 kilojoules. Unit check, kilos, leaving us with kilojoules. All right, so Q total for the second part here are just these 4 contributions added together. 1, 2, 3, 4. And they sum up to Q total is Q1 plus Q2 plus Q3 plus Q4 equal 1126.3 kilojoules. So the strategy for this kind of exercise is to analyze the text, make sure that you note the right amounts in kilos, the temperature changes, if there are some special things to note, for example, is some of the water evaporating, and then break it down to distinct individual processes that you evaluate one at a time. And when you have evaluated all the relevant processes, then the total amount of energy used, simply the sum of the individual contributions.